Hello and welcome to Principles of Mathematics lesson number 21. In this lesson, we're going to learn about operations on decimals. We'll be looking at concrete models, drawings, and strategies that can be used to develop efficient algorithms for decimal operations. We'll be looking at scientific notation for decimals and also strategies for decimal mental computations and estimations. Here we'll look at a concrete example using base 10 blocks for adding 2.16 and 1.73. Notice that since we are only going to the nearest hundredths in each of these, or rather to the hundredths place, we only need to use flats as our units. So then longs will represent tenths of a unit, and the units, the cubes themselves, will represent hundredths in this particular presentation. So 2.16 or 2 and 16 hundredths can be represented with 2 flats, 1 long, and 6 units. And 1.73 or 1 and 73 hundredths can be represented using 1 flat, 7 longs, and 3 units. So then we can just combine those. We have 2 flats here and 1 here to give us 3 flats, 1 long here and 7 longs here. That'll give us 8 longs or 8/10, and 6 unit cubes, and a 3 here will give us 9, or notice that the cube here represents hundredths, so 9 hundredths. So that's how we end up with 3.89, because it's 3 wholes, 8/10ths, and 9 hundredths. So it's a nice visual for showing younger students how decimals work, or rather decimal operation of addition. Notice that we can also handle it in this manner using more familiar operations, such as 2.16 can be written as 2 plus 1/10 plus 6 over 100 in its expanded form, and 1.73 can be written as 1 plus 7/10 plus 3 over 100. So now we just go ahead and combine the units. Of course, we can add in any order because of the commutative and associative properties of addition. So we put 2 plus 1 together, we'll group 1/10 and 7/10 together, and we'll group the 6 hundredths and the 3 hundredths together. And we end up with 3 here for the wholes, and then 1/10 and 7/10 will give us the 8/10, and the 6 hundredths and 3 hundredths will add up to 9 hundredths. Again, we realize that that's going to be 3.89. So another approach to the same problem. We have a very nice and effective algorithm for multiplying decimals, and what's nice about it is that basically we're going to temporarily ignore the decimals, go ahead and multiply the numbers as if they were whole numbers, then we'll adjust for the decimals in a way that I will show you in a second. So let's go ahead and just multiply 6.62 and 143. So it's easier if we write the larger number on the top. So I'll just put 143 first, and we're going to multiply by 62. So 2 times 3 is 6, 2 times 4 is 8, and 2 times 1 is 2. 6 times 3 is 18, so we move 1 over and we put the 8 here and 1 here. So 6 times 4 is 24, and 1 is 25. We put the 5 there and a 2 up here. 6 times 1 is 6, plus 2 will give us 8. So if we go ahead and add, we get 6. 8 and 8 is 16, so we have a 1 here. 1 and 2 is 3, and 5 is 8, and another 8. So we get 8866. So now all we need to do is we need to count how many digits we have after each decimal. We notice that in the first one we have 2 digits. In the second one, in the first one we have 1 digit, for a total of 3 digits after the decimal. So in our final answer, we go ahead and start at the very right past the 6. That's where the original decimal is, and we move it 1, 2, 3. And that basically is going to be the result of that multiplication. And the nice thing is we didn't even need to worry about the decimals till the very end. Of course, there is no mystery as to why this algorithm works, because notice you can take the 6.2 and think of it as 62 over 10, and you can take the 1.43 and think of it as 143 over 100, right? So when you end up multiplying these two numbers, you're going to end up with a denominator of 1,000. That's why you would want to move this decimal 3 places to the left. So that's the reasoning behind the algorithm and why it works. So for this next one, make sure you try it on your own before you watch me do it, because you know what you need to do now. All right. So notice that if we ignore all decimals, we get 13 times 2, right? Which is a simple 26. And now we start with 26. We notice that the first number has 2 digits after the decimal, and the second number has 3 digits. Of course, even if this one had a bunch of zeros after it, remember, you don't count those terminating zeros. All right, so basically we're going to start right after 6, to the right of 6, and we're going to move back 1, 2, 3, 4, 5. So when we run out of digits, we go ahead and fill in with zeros. And that's where the new decimal will be. All right, so the result is basically 0.00026. If you wanted to write it as a fraction, you would have 26 over 1 and as many zeros as you have digits here. So 1, 2, 3, 4, 5. So if you wanted to read it properly, you would say 26 hundred thousandths. All right, so try that with a couple of numbers for yourself. You can always check your answer on a calculator to see if you've done it correctly. Now, multiplying by powers of 10 is a much simpler process. Basically, all you have to do is take the number that is being multiplied by a power of 10 and move its decimal place as many places to the right as you have digits, zeros in the power of 10. Now, we did this with division. Remember, for that one, you have to move to the left. When you multiply by a power of 10, you're going to move to the right. So basically, start with your 3.6. Now, this one will be the prepping part. We'll write the correct answer properly. So we'll move 1, 2, 3 to the right. So the decimal is going to move from there to here, and we can see that the result will be 3,600. All right, that's how you do those. Normally we like to present our answer with as many of what's called significant digits as in the original computation. So this one had 1 decimal place to the right, 1 unit to the right of the decimal place. So you would actually present it as 3600.0. That way they know the level of accuracy of the measurements. We'll get into that a little bit toward the end of the video as far as significant figures are concerned, or significant digits. Now, what would happen if you multiplied 1,000,000 by 3.6? See if you can quickly figure that out and then come back. Okay, so we'll do the prep first. So we're going to take 3.6 and we're going to move its decimal 6 places. Remember, as many places as you have zeros in the power of 10. So 1, 2, 3, 4, 5, 6, right? Fill in the zeros, and there will be your answer. So we have 1, 2, 3, 4, 5. So 3, 6, and then 1, 2, 3, 4, 5. and then we put the point 0 to indicate the significant digits as far as computations. And now we have, if you want to read it, of course, start on the right and count every 3, put a comma, so you can see that's 3,600,000. Next, we want to look at a concept called scientific notation. Now, scientists often run into numbers that are extremely large, such as the example here, the distance that light travels in 1 year, which is near 5,872,000,000,000 miles. So in order to make life a little bit simpler, we use a notation which is called scientific notation. And in using scientific notation, this can be written in this more compact form like that. Now, we'll find out why that happens in a minute, but just to give you a motivation for why scientists use scientific notation. And here, for example, we can take this number and turn it into that. So let's see what scientific notation is exactly. All right, we say that a real number is said to be in scientific notation if it's written in the following form. We have a times 10 to the n, so we have some number times a power of 10. Now, there are restrictions on the number and on the exponent, for which is the power of 10. The absolute value of the number needs to be between 1 and 10, left inclusive. That means it can be 1, but it can't be 10, right? So it can be greater than or equal to 1. So 1 is okay, but it has to be strictly less than 10. So 10 would not be okay. But 9.99, no problem, because it's less than 10, right? And we want this exponent to be an integer. And that's the rule that we're going to use. Now, here are some examples of numbers that are in scientific notation. 2.5 times 10 cubed, negative 9.9 times 10 to the negative 7. Notice this part is between 1 and 10, left inclusive, and the exponent is an integer. Now here, yes, there's no problem with that negative. That's why we said the absolute value of the number needs to be between 1 and 10, left inclusive. And of course, the absolute value of negative 9.9 is 9.9, positive 9.9, which is less than 10. So we're okay. And notice negative 7 does belong to the set of integers. Remember, the set of integers is the set composed of all the negative whole numbers, the opposites of whole numbers, 0, and then all the positive whole numbers. Okay, so negative 7 is fine. Here's another example of a number that's in scientific notation, a simple 1 times 10 to the 0. Now, notice that on this other side, I have the same number as far as value is concerned, because 10 to the 0 is 1, 1 times 1 is 1. But we consider this to be the scientific notation version of this number in standard notation. So you have to distinguish between the two types of notation. Now, this is neither in scientific notation nor in standard notation. A standard notation, of course, being just a regular, for example, in standard notation, this would be 25,000, right? So, but some people kind of look at that and they can fall into the trap of thinking, oh yeah, it has the general form of a scientific notation. Yeah, but the problem is this number here is not between 1 and 10, left inclusive, all right? Left inclusive meaning the number on the left can be part of the numbers you're looking at, the number on the right cannot. Here's another one, 0.5 times 10 to the 25. We run into the same problem. 0.5 is not in this zone where it's supposed to be. Greater than or equal to 1, less than 10. Okay, let's see if we can come up with a nice algorithm for how to write a number that's given to us in standard notation into scientific notation. So the procedure is going to be very simple. You're going to start looking from left to right, okay, always in that direction. And you're going to stop after the first non-zero digit. So here, of course, that number is 4. So we're going to go ahead and move the decimal place right there after the 4. Now, because I put a decimal place here, these zeros aren't really going to matter once I write them in here, right? So I don't need to write them. However, when I try to figure out what exponent I need for the 10, of course, these zeros need to be counted. So notice that we moved the original decimal point 1, 2, 3, 6, 8 places to the left in order to accomplish or to obtain this number, right? So that's basically the same thing as saying, let me explain to you why this algorithm works. So by moving it 8 places to the left, it's like as if we divided by 10 to the 8, right? But remember, we're just changing the way the number looks. We don't want it to be a different number. So in order to compensate for what we have done here by dividing by 10 to the 8, we're going to multiply by 10 to the 8, okay? So we get 10 to the 8 right there. That's why the procedure works, okay? So this is the reasoning behind why it works. So remember, if you move the number to the left, the decimal point of the original number to the left, you're going to end up with a positive exponent to compensate for that movement to the left, right? To keep the number the same. So in other words, remember, these look different, but they represent exactly the same quantity, right? All right, so we're going to follow the same procedure for this one, but this time notice the original decimal, as we move from left to right, for the first example, the decimal landed right there, right? For this one, the first non-zero digit is 2, so we're going to move the decimal right there after the 2. So we're going to end up with 2.31 times. Now, in order to move this decimal place 1, 2, 3, 4, 5 digits to the right, I basically took that 0.000231 and multiplied it by 10 to the 5, right? Because I moved the decimal 1, 2, 3, 4, 5 places to the right, right? So to compensate for that, I need to go ahead and divide by 10 to the 5, right? So notice that's the same thing as saying multiplying by, I could have also said this in this way. I could have said 0.000231 times 10 to the 5 times 10 to the negative 5. Remember the rule that if you have x to the negative n, that's 1 over x to the n. That's the rule we're using. So here we realize that in order to be able to do this, to move the decimal 5 to the right, we have to compensate by multiplying by 10 to the negative 5. So let's remember, when we move the decimal of the original number to the right, we're going to need a negative exponent on the for the power of 10. Now notice 10 to the 5 times 10 to the negative 5 using the product rule gives me 10 to the power of 5 plus negative 5, or 10 to the 0, which is 1. So you see, that's why the original number and this number are basically the same. All right. What about the next one? Well, for the next one, we move from left to right and stop after the first non-zero digit, which is 8. So we get 8.37 times 10 to the, okay, which way did we move the original decimal? We moved it to the left, right? That means we're going to need a positive 1. How many places? 1, right? So we just need a positive 1. All right. For this one, remember, with the negative, just carry the negative and deal with it as if the negative weren't there. So we get the first non-zero digit is 1, so we put the decimal here. So we get 1.0, or you can just put 1 times, now let's see, how many places did the original decimal have to move? 1, 2, 3, 6, 7, right? So because we had to move it to the left, the exponent is going to be positive 7, just like that. So remember, a movement of the original decimal to the left results in a positive exponent for the power of 10, and moving it to the right, the original decimal, will result in a negative exponent for the power of 10 in order to keep these things balanced so that the two numbers are indeed equal. And that's how you do these. And of course, we could have written all of them using just a dot, but it is commonplace to bring the multiplication symbol back for scientific notation. So you could have just written 4.13682 and then just use the dot notation times 10 to the 8. Or we could have said 2.31 and then the multiplication dot times 10 to the negative 5. Or here 8.37 times 10 to the 1, which we can just leave as 10. And this one we could have just said negative 1 times, actually I wanted to change that to a dot on the last one, and the same with this one, times 10 to the 7, like so. Okay? So that's how you handle going from standard notation to scientific notation. In this next example, we're going to go the other way around, and we're going to take a number that's in scientific notation and convert it to standard notation. So this is actually the easy direction, because basically all you're doing is taking like 6.84 and multiplying it by this power of 10. Of course, we know that we can write this as 6.84 over 10 to the 5, because remember, x to the negative n equals 1 over x to the n. So we get 6.84 times 1 over 10 to the 5. Of course, this is over 1, so you can just multiply it, 6.84 and 1, you get 6.84 over 1 times 10 to the 5, which is 10 to the 5. That's why it turns into this. And of course, we know that that means 6.84 over a 1 and 5 zeros, right? So we know that when we divide by this power of 10, which has a 1 and 5 zeros, we're going to move the decimal 5 units to the left, 5 digits to the left. So we start with 6.84 and we move the decimal 1, 2, 3, 4, 5 and place the decimal there. So that's what we end up with. So 0.000684. Of course, at that point, we go ahead and erase the first decimal, and there's our answer. So, of course, you don't have to go through all this once you get a hang of this, because you realize that when you multiply a number by 10 to the negative 5, basically you're just going to move the decimal 5 to the left. So normally we just go from this to the final answer once we're comfortable with this. The same goes with positive exponents. So except that in this case, we would, like for example, with 3.12 times 10 to the 7, we would move the decimal point 7 places to the right. So we start with 3.12 and we move the decimal 1, 2, 3, 4, 5, 6, 7, right? So when we run out of digits, we add zeros. So the decimal is now here. We go ahead and erase the original decimal and we're done. So there it is. Now, of course, if we start up from the right side and then put commas every 3 digits, we would end up with 31,200,000. Okay, so for this next one, Negative 4.08 times 10 to the 4. We know that the negative just carries, and we handle the 4.08 times 10 to the 4 in the same way. We write the 4.08. Go ahead and move the decimal 1, 2, 3, 4 units to the right. So we put zeros when we run out of digits. Erase the original decimal, and there is our value. So negative 40,800. All right, and that's how you go in the other direction, from scientific notation to standard notation. Okay, so most scientific calculators have a button similar to this. It may not say exactly EE, but that usually indicates the scientific notation button. So the way you use it is the following. Let's say we want to multiply these numbers, right? So I'm going to go ahead and use a set of parentheses to contain my first number, which is 5.2 times 10 to the 6. So I just type 5.2. Now notice that on this calculator, which is the HP prime, it says EEX, right? So we click that, you get an E on the screen. So what the E represents is times 10 to the power of, and instead of typing the times 10 to the power of, you just type in the exponent and the calculator takes care of the rest. So you would just put in 16 and make sure you exit the first set of parentheses, and then we can open another one and type in the second number. So 9.37, and then click that EEX button again, and then type in 4. When you see that, that means 9.37 times 10 to the 4. And then you hit enter, and that gives you the answer also in scientific notation. So 4.8724 times 10 to the 21 is what your answer would be. So 4.8724 times 10 to the 21. Okay, so that's how you would use a calculator for scientific notation. All right, so when it comes to dividing decimals, I don't want you to worry. We're not going to do a bunch of decimal divisions, but there are some clever tricks I want you to be aware of. So for example, let's say you want to divide this 128.6 by 4. So what you could do is kind of avoid decimal division altogether. So you start with the 128.6, which you're dividing by 4. You can write it as a fraction like that. Now, I'm going to go ahead and multiply top and bottom by 100. So notice that I end up with 128, and you're going to move the decimal point on this one 2 places. 60 over 4. Now remember, this multiplication is taken care of now, right? So what you're left with is a 1 and then over 100, right? So if you take a look at that 12860 and divide it by 4, we know it's divisible by 4 because remember, the last 2 digits form a number that's divisible by 4, and that's the divisibility test by 4, right? So you end up with 3,215 over 1, which we don't need to write, right? But what we can do is this times 1 over 100, we can bring the 100 underneath there. So this part just became 3215, and then we have times 1 over 100, which is the same as divided by 100. And that, of course, can easily be handled because we take 3215 and move the decimal point 2 to the left. So we get 32.15. So tricks like that can help you handle some decimal divisions very quickly. Like if you have a simpler example, which is also good to know. Let's say you have 2.4 over 0.8, right? Notice that in this case, if I just multiply top and bottom by 10, I just end up with 24 over 8, which is what? 3. We didn't have to do any kind of decimal division at all. All right, there are some mental computation techniques that are good to have in our arsenal. And some of the techniques we've already used with whole numbers, we can use with decimals as well, such as breaking and bridging. So notice here, we want to add 1.5 and 3.7. So we go ahead and take care of the 1.5 plus 3, just the whole number part. That gives us 4.5. That leaves us a 0.7, which we make sure we bring down, and then plus 4.48, right? Now, the sum of these two is going to be 5.2, right? So once again, we just take the 5.2 and add it to the whole number part here, which is 4, so we get 9.2, and then we just have to add the 0.48, so we get 9.68. So this is called breaking and bridging. Then we also have the compatible number technique. If two decimal numbers can add up in such a way that their sum becomes a whole number, we consider them to be compatible. So we notice that here, these two, for example, add up to 12 because 0.91 and the 0.09, they add up to 1, right? 7 and 4 is 11, 11 and 1 is 12. And we notice these two, for example, add up to 4, right? So it's just a matter of being aware of these scenarios when they come your way. You're obviously not going to meet these scenarios all the time, but it's good to be aware of them when they do come your way. Here's another method we already saw with whole numbers as well, making compatible numbers, like 9.27 and 3.75. I know that a nice number close to that is 9.25, and a nice number close to 3.79 is 3.75. Now, those two can easily be added to give us 13, and then we just have to take care of that sum, which is 0.06, so we get 13.06. In this subtraction here, we notice that if the 1.97 was actually only 0.03 more, I would have a nice 2.0. But notice that here, I would have to factor out the negative, so I'm actually subtracting a negative 0.03 here. So that's why we need to add it up there to balance it out so that the problem is not changing, it's just changing the way it looks, right? So then we end up with 4.66 minus 2, which is easily handled as 2.66. Here's another technique which we call balancing with decimals. Notice that if you multiply the 0.25 by 4, we know we get the nice whole number 1, right? So as long as we take both of them and multiply them by the same number, it's exactly like saying taking a fraction and multiplying the numerator and denominator by the same thing. So that's all we're doing. And we know we can do this, right? Because we're just multiplying by 1. So then we end up, instead of this 8 divided by 0.25, we end up with the much nicer 32 divided by 1, which we know is 32. All right, rounding with decimals is something I'm sure most of you are familiar with, but we'll look at a few examples just to remind you. Let's say we want to round to the nearest hundredths, right? So the first thing we need to do is locate the hundredths digit, right? So we know that we go 1, 2 places to the right of the decimal. That's where the hundredths digit is. So once you've located it, though, then you have to look to the right. So you look to the right, and if that number is 5 or higher, you round up, right? And if it's 4 or lower, you go ahead and round down. So how do we round up? We round up by just adding 1 to that digit and then dropping the rest, right? So we get 7.46. This is rounded to the nearest hundredths. We rounded up because this was higher than 5. For this one, if we want to round the same number, we're rounding to the nearest tenth. So the 10th digit is right there, the 4, right? So we have to look to the right. That's a 5. Remember, 5 also is one of the digits that forces us to round up when it's to the right of the digit we're considering. So this is going to become 7.5 when rounded to the nearest 10th. Now, if we want to round to the nearest unit, the unit digit is right there, the 7, right? So when I look to the right of it, that's a 4. So that means we're going to round down. So that means the way we round down is we keep the original digit that we were rounding to and then chop the rest. They all become zeros, right? Now in this case, because it becomes 7.000, we can just write 7. All right, so let's keep these straight. This is 7, this is this one, this is this one. Now 7,456, we want to round this to the nearest 1,000. We know this is the ones, this is tens, this is hundreds, this is thousands, right? So this is the digit we want to round to, and we look to the right of it, it's a 4, so we're going to round down. So this time, this stays 7, and they all become zeros. But these zeros don't go away because they're before the decimal, right? So this rounded to the nearest 1,000 just becomes 7,000. 745, we want to round to the nearest 10. Now we know this is the units digit, this is the tens digit. So we stop there, then we look to the right. When we look to the right, that's a 5. When it's 5 or higher, we round up, right? So this becomes a 5, and that becomes a 0. So this rounds to 750 to the nearest 10. Now this 74.56 rounded to the nearest 10. So here's the ones digit, here's the tens digit. We look to the right, that's a 4, so we're going to round down. So the 4 becomes a 0, so we get the 7 stays as is, so 70.00, right? The rest all become zeros, so we don't need to write that, so it's just 70. All right, a few facts to keep in mind. Estimating decimal computations using rounding. Rounded numbers can be useful for estimating answers to computations. We already know that. When computations are performed with rounded numbers, the results may be significantly different from the actual answer. Other estimation strategies, such as front-end clustering and grouping to nice numbers that were investigated with whole numbers, also work with decimals. And what about round-off errors? Well, round-off errors are typically compounded when computations are involved. When computations are done with approximate numbers, the final results should not be reported using more significant digits than the number used with the fewest significant digits. Significant digits or significant figures, they're also referred to as, basically work out as follows. Non-zero digits in a number are always significant. Zeros before other digits are non-significant. Zeros between other non-zero digits are significant. And zeros to the right of a decimal point are also significant. To avoid uncertainty, zeros at the end of a number are significant only if to the right of a decimal point. All right, let's take a look at a short video that does a nice job on this. So let's go together and check that out.
Welcome to Moo Math and Science. In this video, I'd like to go over the rules for significant figures. You may have been asked before, how many significant figures are in a number like this? Once I go over the rules, I think you'll have a little better understanding of figuring out significant figures. First, the rules. Number 1, count all non-zeros. Like the numbers 2, 3, 4, 5 are all non-zeros. 2, count zeros that occur between non-zeros. 3, leading zeros are not significant. For example, 0.004, the zeros are not significant. Trailing zeros are zeros at the end of a number. If there is a decimal, count them. The way I remember this is that zeros always need a decimal to help them. And then finally, if there's no decimal, do not count the trailing zeros. So let's get started with a couple examples, and I have the rules here to remind you. 53. This one's fairly straightforward. They are all non-zeros, the 5 and the 3, so you will have two significant figures. Next, 203. Again, you have two non-zeros, the 2 and the 3, but you have a 0 in between, so you will have 3 because you will count them all. Next, we have one with some leading zeros. Remember the rules, leading zeros are not significant, so you will not counting until you get to the 9. So you will have 3 significant figures. Next, we have 23,000. Okay, let's look at the rules for trailing zeros. There is no decimal, so you do not count the trailing zeros, so you will have 2. Next, we have this number, 1.0040. Well, you have two non-zeros, so you know you will count these. Then you have two zeros between non-zeros, so we will count these. And then we have a trailing zero, but remember the rule for trailing zero. A trailing zero must have a decimal, and you do, so you will count all of them. So that will be 5 significant figures. And the last example, this one looks pretty straightforward, can be a little tricky. You have 90, so you have a non-zero, the 9, and you have a trailing 0. But notice there is no decimal, so you will only count the 9, so you will only have 1. So I hope that helps in significant figures. Thanks for watching, and Moo Moo Math uploads a new math and science video every day. Please.
All right. So
Subscribe and share.
with that nice presentation, we come to the end of this lesson. So we'll do our usual practice of looking at a few homework problems now. All right, so here we have a simple problem that can be handled using a proportion. A US $1 bill was valued at 8,458 10,000 Swiss francs on a particular day. What was the value of $39.35 in Swiss francs on that day? So you can actually set up a very quick proportion. You can say $1 is to 0.8458 francs as 39.35 dollars is to how many francs, and you just solve it. So now cross multiply, so x times 1 gives us x, and we're going to get 0.8458 times 39.35, and of course the units will be in francs, Swiss francs, right? So we just go ahead and take care of that multiplication. So 0.8458 times 39.35. Now, when it comes to money, we basically don't need to worry about anything beyond the nearest hundreds, right? Because like even with dollars, we only have cents, so we go to the nearest hundreds. So notice that the digit to the right of the hundredths digit is a 2, so we're going to keep the 8, chop the rest, right? So that's where we get, this is going to be, of course, approximately. So we say either about or approximately 33.28 Swiss francs. Okay? If you're going overseas, it might be handy to know how to do something like that quickly. All right, here's a problem that you can quickly do in your head because we're so familiar with money, right? So Iris worked a 20-hour week at $7.25 per hour. Mentally compute her salary for the week. So notice that we can just take care of the 20 times 7. That gives us 140, right? Then we basically need to figure out how much 20 quarters are, right? 20 quarters. Now we know that 4 quarters is $1. So 20 quarters would be 5 times that, so it's $5. So we have a total of what? She made a total of $145 that week. All right, so here we have a problem. Steve drives at a constant speed of 51.6 miles per hour. How far should he expect to drive in 3/8 of an hour? So this is a situation in which you do need to know the basic formula for which connects rate, time, and distance. And of course, it's the famous RTD formula. We know rate times time equals distance, right? So the rate is 51.6 miles per hour times 3/8 of an hour. Notice that your units should always work out, right? And here we notice the hours will cancel out. We'll be left with miles, right? So all we need to do is calculate that 51.6 times 3/8. So we have 51.6 times, I'm going to use parentheses here, 3/8. And we end up with 19.35. And of course, that's in miles. Okay. All right, so in this problem, we want to know how much greater is 0.62 times 4 than 0.61 times 4. So this actually can be done without really multiplying in the following way, right? Notice that I can take that and write it as 4 times 0.62 minus 4 times 0.61. That's going to be telling me how much greater the first number is than the second number, right? So, and notice I just wrote these in the other order because of the commutative property of multiplication. I can do that. We didn't have to, it just looks a little nicer. So now, notice you can factor out a 4 by using the distributive property in reverse. So we get we're left with 0.62 minus 0.61. Now we know that that's just 0.01, so we can quickly get to the answer. Remember, to multiply 4 and 0.01, just multiply 1 and 4, which gives you 4. Then you have 2 digits after the 0 here and none here. So you're just going to move 2 digits to the left, and you're going to get 0.04. So this product is larger than that product by this amount. All right, let's look at one more problem before we call it the day. Jamal wants to know why 0.3 and 0.30 are equal. How would you explain that to Jamal? Well, one way is to, of course, explain to him that trailing zeros do not count, right? But what if that didn't do it for him? He wanted more explanation. Well, just remember the number 0.3 is just 3/10, right? Whereas 0.30, if you really want to write it out, is 3/10 plus 0/100. And of course, 0/100 is what? 0, so you end up with the same, what? 3/10. So this is really, I mean, you can do this with as many zeros that trail as you want. You're going to have the same situation. If you add one more 0, you would add plus 0/1000. Same thing, right? So that's why we really don't count the trailing zeros. All right, that should do it for this lesson. You take care, and we'll see you for the next lesson.